Welcome to Chemistry 111. Hopefully you guys are being safe, not sliding on the ice. I still have 3 tests left to be turned in, so we will not go over the test crib just yet. Most of them are turned in, pretty good average. I haven't updated scores because I haven't calculated what I'm going to do for a curve just yet, but it's so far pretty good. But in the meantime, we'll go ahead and go to chapter 5. Then probably look at some of the homework related to chapter 5. Chapter 5 is not particularly too long of a chapter. So let's continue from where we were leaving off. Okay, so we had previously talked about effective nuclear charge, and that had to do with both as the proton count went up, effective nuclear charge usually went up, especially as we moved across the row. As we moved across the row, the effective nuclear charge went up because the valence electrons did a very poor job of shielding each other from the additional protons. However, when we went down a column, effective nuclear charge went up only slightly, and that had to do with we added a new level of core electrons that are more effective at shielding the valence electrons. Then we finished up last class by talking about how that relates to the atomic radius. As we move across a row, the size would decrease. That's because additional effective nuclear charge meant we could pull the layers in closer. But as we move down a column, the increasing Z effective could not counteract the additional core electrons. Every time we added a new layer of electrons, they started farther out. Even though they got pulled in a bit by the Z effective, the net change when we add another layer was further apart. So that things like francium are going to be the biggest elements, and things like fluorine are going to be the fluorine and helium and neon are going to be the smallest elements. That's where we had ended on Wednesday. Well, the next thing we can look at is ions, the atomic radius of various ions. And so if we're talking about size, that the neutral thing, it's decreasing when we have a greater Z effective and increasing when we add layers. So how does removing or adding electrons change this radius? Now remember, as we make an ion, the number of protons are not going to change. And the number of protons are constant for a compound, for an element. The number of protons determines what the element is. And if the size is related to the electron cloud, how will decreasing the number of electrons in that cloud or increasing affect the size? So cation, when you cation, we are losing an electron. As we lose an electron, essentially we're going to allow that electron cloud to shrink. The electron cloud is shrinking because, one, the electrons are having a less repulsive effect. They're not pushing each other as much because we have less electrons there. And two, the the valence electrons, while they do a poor job of shielding each other, they do shield each other just a little bit. And as they lose a valence electron, each electron is now feeling a stronger Z effective. Each time we lose an electron, the proton can pull the remaining electrons that much tighter. And eventually we'll get to a point where we completely remove the core. If we completely remove completely remove the valence electrons. If we completely remove the valence electrons, we actually see a huge drop in size, because that we essentially remove that outer layer that made it so big and bulky. So we actually see cations are oftentimes really, really small, especially things like lithium and beryllium, sodium, magnesium. Those were really big in the last slide. On this slide, they're actually rather small because we've removed that outermost layer. So potassium +1, calcium +2. Typically speaking, the larger the positive charge, the smaller it is. If I'm comparing potassium to calcium to gallium, for example, gallium is going to be a little bit smaller than calcium. Aluminum should be a little bit smaller than magnesium because 1 plus, 2 plus, 3 plus. And the opposite is true for anions. For anion, when we put in another electron, essentially you have a greater repulsion. So the other electrons are bouncing into each other, forcing them further apart. You have better shielding, so the Z effective can't hold them nearly as well. And essentially, the more electrons we add, the larger the negative charge, the bigger it is. Such that, like, typically lithium neutral and fluorine neutral, lithium was bigger than fluorine. But now, as we look at lithium positive and fluorine negative is bigger than like sodium positive. Fluorine negative is bigger than trying to think. It might even, I can't read the numbers right now, that's kind of small on my screen, but it may even be similar size to potassium positive. Fluorine negative is pretty big. Oxygen 2- is even bigger. Nitrogen 3- is bigger yet. Because of this, the negative electrons repel each other, they push themselves out, and the Z effective is weaker because of that. It's like you're trying to carry like 5 bags of groceries into the house. Your hands are full, then someone hands you something else so they can get the keys out of the pocket to unlock the door. You're already having a hard time holding the bags, and now you have one more thing. Well, there's a good chance you're going to drop them all. You're just not able to do it as much. So all things considered, anions are almost always bigger than cations. Almost always. But the larger the negative, the larger it is. And for isoelectronic atoms, you can arrange them in increasing size based on the negative charge. So remember, isoelectronic were ones with the same number of electrons, but different number of protons. N3-, O2-, F1- all have 8 electrons. Sodium +1, magnesium 2+, aluminum 3+, all have 8 electrons. So I could put aluminum as the smallest and work my way magnesium, sodium, fluorine, oxygen, nitrogen in order of increasing size based on this isoelectronic series where the number of electrons are the same, but the charges are different because the number of protons are different. Now, so that is just one trend we'll look at that has to do with a lot of the properties. Now, ionization energy is the next trend we'll look at, which has to do with how easily an atom will give up its valence electrons. So how easily is it going to be to make a cation? What energy does it take to ionize this? What energy does it take to eject an electron? When we looked at the photoelectric effect back in chapter 4, we briefly discussed it. If you shine lasers on a metal, sometimes you can get them to eject electrons based on the wavelength of light. What we were doing there is ionizing the metal. We were making an electron escape and thus making it a cationic. That was an ionization energy we were essentially calculating. And so ionization energy is literally the energy required to remove a valence electron from a gaseous atom to form a gaseous ion. So if I had lithium vapor, how much energy would it make it, turn it to make it lithium cation vapor? And you can calculate that energy. Typically, atoms with low ionization energy will not bind their valence electrons very tightly. Atoms with low ionization energy will be highly reactive for that reason. All reactions will have a small amount of energy to make them run. Many reactions will produce more energy than the initial input. But all reactions have a small startup cost. The lower the startup cost, the easier it is for them to react. Some of these metals, you put them in air, they can extract the energy from the ambient temperature and will naturally react with the air. You put something like a block of sodium out in the air, you scrape off the oxide layer, and it will oxidize readily in air without any outside force, which is why things like sodium metal stored under oil, where there's like no air and no water. If you put sodium in water, it's going to rapidly react, like fizzing and popping while it does it. Now, how do we look at the trends? The typical trend has to do with both Z effective and atomic size. So remember, Z effective went up as we crossed the table, and Z effective went up just a pinch as we went down the table. But size went down as we went across the table, and size went up when we went down the table. So the trend for ionization energy is ionization energy decreases moving down the table. Because to remove the valence electron, we have to pull the electron from the outermost layer. Well, when we move down the table, the atoms got bigger and bigger and bigger. And so as we moved down the table, the electrons were further and further from the nucleus. They're easier to escape. They're farther away from the core, so it's easier to pull them out. They don't have to go as far, and they're not being held as tightly. You have a kid being micromanaged by a parent, it's going to be pretty hard to escape. You have a kid that's kind of able to roam the neighborhood without really being watched. It's a lot easier for the kid to get lost or to go somewhere they're not supposed to. The same thing, the electrons that are farther from the nucleus have an easier time being pulled away. Well, the ionization energy will increase as we move across the table. That's because, remember, size was decreasing and effective nuclear charge was increasing. So not only is the nucleus stronger to pull them in, but they were also closer to the nucleus. So not only is it a more strong-willed parent, but it's also they're being watched more carefully from a closer distance. So in general, things like calcium, things like cesium will have the highest ionization energy. Things like the noble gases and fluorine and chlorine and bromine, the halogens, are going to have the highest ionization energy. So cesium takes the least amount of energy to work. Fluorine and the noble gases take the most. You see right there, helium is that really high one in the top right corner, followed by neon and then fluorine and then argon. Now there's some kind of hitches to this perfect trend, and that has to do with being full. There's a certain amount of stabilization energy with being half full in orbital. So nitrogen with its 2p3 half full orbital makes it harder to remove an electron than oxygen, where it's 2p4. It'd rather unpair the electron, and so it actually gets a little bit easier to lose an electron from oxygen. Same thing with beryllium versus boron. Boron, it's easier to lose that one electron for the 2p1 than it is to unpair the boron lose the 2p1 than it is to lose the beryllium 2s2. Now there is a trend with ionizations and energies, because it's possible to lose more than one ionization, or lose more than one electron. As it is, when you lose one electron, it becomes a singular cation. When you lose a second electron, it becomes a double cation. But what does that mean about the energy? Each time you pull an electron off, the energy will increase. Because what happens? Remember, when we became a cation, the size decreased and the Z effective went up. So the electrons become more carefully watched and they get closer to the nucleus as that happens. So each time we remove an electron, the ionization energy will increase. However, we will see a massive increase when we go from valence level to core level. When we lose all of the valence electrons, the next step is we go down to the next energy level, and if we try to remove that next energy level, we see a huge increase in ionization energy, because looking at the difference between the valence and the core is looking at the difference between, like, say, 10 feet away and suddenly jump down to 5 feet away. Suddenly it's that much closer and that much harder to remove the electrons. So you can actually tell what an element this is just by looking at its ionization energy. Just by looking at its successive ionization energies, you can tell what element it is, because you can tell how many electrons it has in its valence. So just looking at lithium. Lithium's first ionization energy is 520 kilojoules. Its second, which would be removing a core, jumps from 520 to 7,298. The third one, which would be the completely emptying out all of its electrons, jumps to 11,000. Now beryllium, remember, as we go across the table, ionization energy increases. Beryllium is 899, so it's jumped up by a factor of what? Maybe like 300, 400. The second ionization energy is 1757. It's practically doubled, increased by a factor of 900, increased by maybe another 900 from the first to second. but from 1757, it jumps to 14,000. That's a rather large jump. This one, it doubled. This one, it maybe increased by a factor of 9 or more, 9 or so. And this third ionization energy is 21,000. That's jumping another, what, like 7,000. So not jumps about 12,000 and another 9,000 or so. But, well, 7,000. So really huge jump to get to the core. Boron, which I said is one of those weird ones, 800, then 2427. So kind of biggish increase by 3 or 4. Then it goes to 3660, increase of about 1,000, and then it goes from 3660 to 25,000. Increasing by a factor of 1,000, 2,000 kilojoules is a small jump. Increasing by a factor of like 20 kilojoules or 19 kilojoules, 90 kilojoules. So that's that huge jump. Carbon, as you see, 1, 2, 3, 4, like about a 2,000 jump, and then we goes from 6,000 to 37,000. A huge jump. Same thing with nitrogen. Even though nitrogen would rather be 3 minus, you can calculate the energy it would take to remove the electrons. Same thing with oxygen. Same thing with fluorine. By the time you remove the 7th electron of fluorine, you're up to 17,000 joules per electron. So you're carrying 1680, 3370, 6050. There'd be the sum of all these numbers. But still, that next loss becomes 9,000, 90,000. It's such a huge jump, you're not going to see that jump. It's too big of a cost. There's a certain point where you can't pay it. See, neon, big jumps, but not as big as 23,000 to 115,000. So you can tell what column an element is in based on where that big jump is at. You can tell all about this by just looking at where this big jump is at. And that has to do with going from valence to core. Now, another trend would be essentially just the opposite. It's opposite in almost every aspect. Electron affinity, if ionization energy is the energy cost to remove an electron, electron affinity is the energy gained to put an electron in. We'll go, and it's practically the same. It's practically the same as the previous trend. Of course, this is practically the same because we're looking at a cost versus a rebate. We're looking at the energy rebate. So if cesium was the lowest cost to remove an electron, and like fluorine and neon were the highest cost to lose one, you're going to have elements like cesium being one of the higher costs, or the lowest rebate to get an electron, and fluorine being the highest rebate to get an electron. So as we go down the table, there's a gradual decrease in electron affinity, that we get less and less by putting an electron in. Now, this is only a gradual decrease because of there's opposing forces of while the size gets bigger, there's also decreased electron repulsion when we put electron in there. So even though the Z effective is less effective, there's less repulsion, so there's less of an energy negative. But as a trend, as we move across the table, the electron affinity increases because higher Z effective means we get more bonus when we put an electron in. Now, this is a very weird trend. Some of these guys will buck the trend, and that's due to the half-filled shells. That there's a certain stability of being a half shell that will make it either hard to remove an electron or hard to put one in. So you'll see things like lithium, beryllium, boron drops down, then up to nitrogen. Nitrogen's higher than oxygen, and you keep going up. You see that zigzag pattern with ionization energies. And with electron affinities, you'll see things like lithium actually has some degree of electron affinity, but beryllium does not. That's because to put the second electron, to put an electron into beryllium means we have to go from the 2s2 to the 2p1. There's a certain amount of cost to put that into the 2p1 that is offset whatever benefit we have. So then we have boron and carbon and then nitrogen. You notice the trend is going up until you hit nitrogen, which is suddenly 0 again. Well, nitrogen has 2p3. 2p3 electrons means to put the fourth electron into that 2p means you have to pair them up. And suddenly we go from a half-filled orbital to a paired electron orbital. And so we lose some of the benefit there. And so nitrogen is bucking that trend. But then we go back to oxygen, that's normal. Fluorine, that's normal. And these noble gases. The noble gases have 0 electron affinity. Why? The core of the electrons are filled. The valence is filled. They do not need any electrons to be stabilized. They're going to definitely have 0 electron affinity. So there is a lot of exceptions, and when you do some of the homework, watch out for some of these exceptions. However, I will try not to call you on any of these exceptions on a test, unless I specifically ask you to think about an exception. I'm not going to put a question that's a trick question that says, like, put these guys in order of increasing electron affinity, and then have one like, oh, you should have switched phosphorus with silicon or whatever. So I'm not going to try to trick you on the test, but there are exceptions to the rule because of the nature of these orbitals that we learned all about. So when we look at the homework in a little bit, be watching out for that. Now, the other part of this chapter is looking at different types of bonding. We have, we're going to focus on this chapter about ionic bonding, but next chapter, which is probably for the next test, is going to be dealing with covalent bonding. So ionic bonding, remember, is any time you have a metal and a non-metal together, this is going to be part of an ionic bond. Doesn't matter how many non-metals are in there. A metal and a non-metal is going to have some form of ionic bond. And this is through ionic electron transfer. So we're going to have one atom losing its electron to form a cation, and one electron gaining its electron to form an anion. And this is going to be held together by an electrostatic attraction, these opposite charges. The positive pole and the negative pole of a magnet attract, and then they form this compound. So sodium chloride is just going to be, so sodium has one valence electron. It loses that one valence electron to form sodium plus. Chlorine has 7 valence electrons. It gains that valence electron from sodium. It forms chlorine 1 minus. These positive charge is attracted to the negative charge, and we form a compound that is held together by attraction. Now we're going to just call it sodium chloride instead of this whole mess to try to make it a little bit easier. Aluminum has 3 valence electrons. It's going to lose all 3 valence electrons. Chlorine, since each chlorine only needs 1 electron, each chlorine will only get one of those three, but we need 3 chlorines. So 3 chlorines match with the aluminum 3 plus to form aluminum chloride. The ions will tend to adopt a noble gas electron configuration. Sodium and aluminum would have adopted the electron configuration of neon. Chlorine, in this case, adopts the electron configuration of argon. This is a particularly stable energy. Now, we're going to look at this largely next semester, but these ion bonds are not just simply a single pair. They're actually going to make a huge crystal lattice. This is a small structure looking of sodium chloride. This is a small little snapshot of how this actually looks. Looking from this row to this row is actually what we would call the unit cell, the repeating pattern that's going to happen within a larger crystal structure, where we have these cations in the corners and in the face, and we have these chlorines in the center and in the edges, and you see how each chlorine atom is surrounded by 6 sodiums. And if you kept going the structure left, right, up, down, you'll see every sodium atom is surrounded by 6 chlorines. But not once does a sodium get close to another sodium. Not once does a chlorine atom get close to another chlorine atom. Now, the reason why we usually call these guys formula units is because when we have these millions and trillions of atoms, we cannot simply define it as a singular molecule, but we can simplify it to the empirical formula. If I counted in here, you would simply say, well, there's equal amount of sodiums as there are chlorides in this whole generalized structure. And that's going to be kind of what we're actually dealing with when we deal with all of our crystal structures. Some sort of crazy thing like this. Now, there's a certain amount of energy related with this. Now, we could calculate what it would take to make this. What would it take to make this? So from looking at the generalized structure of, starting here, metal plus halogen gas, what would it take to make this solid? To make this solid, it produces a chunk of energy. Well, we can calculate what that should be. First step, you would have to sublimate the metal, which means to go from solid to gas, melt it and turn it into the gas phase. So what would it take to make the metal a vapor? Then what energy would it cost to make to ionize the metal? Then what energy would it cost to split up the halogen gas into a pure element from a diatomic? But then what energy would we get back to give the electron to the halogen? And you'll see right here, the difference between this spot and down here is a big, big difference in energy. If we calculated all the steps to get to here, the crystallization going from cation to anion is a huge drop. But there's a certain amount of energy that gets stored when I stick these two together. When I form a crystal substance from these two charged ions, we get a huge amount of energy back. And this is called the lattice energy. It's this huge energy savings when we weave together a cation and anion into the patchwork of the crystalline solid. And that's what makes this reaction going from here to here so darn doable, so darn possible. Why we can put sodium and halogen gas and it's going to produce sodium chloride salt and a ton of energy as it does it. because of this magical lattice energy that's going to push this forward. So if our starting point is actually at 2, right here, right between this spot, we get energy out of this system. Now, let's say lattice energy is so strong it'll make the formation of solids a highly exothermic process. But this depends on essentially 2 things: how well the ions will pack together, and what attraction there is between the ions. So the relative charge and the bond distance will control the lattice energy. There is a constant, but we don't really need to consider the constant. We are only looking at this on a kind of qualitative level, not on a pure numerical scale. So in the case of sodium chloride, the charge of the cation is 1. The charge of the anion is 1. And then we'll just look at what is the bond distance between sodium and chloride, and that's going to tell us something about the lattice energy. Well, what does that mean? What does this mean? Well, if I took potassium chloride, for example, potassium is also +1. But what do we know about potassium compared to sodium? Well, potassium is a bigger molecule than sodium, and so there would be a bigger bond distance than with sodium chloride. Or if I said potassium bromide, bromide is definitely a bigger molecule than chloride, even though it's also -1. And so the bigger bond distance means the lattice energy would go down. As the molecules go down the table, they get bigger, and so the size would get bigger, and so lattice energy gets smaller. If the charges go up, the lattice energy goes up. So if instead of sodium, I used magnesium chloride. Sure, magnesium would be a little bit smaller, but the charge would also be 2+. So it would be constant times 2 times 1 divided by size, which is essentially the same. So I've essentially doubled the lattice energy, if not a little bit more. Instead of magnesium chloride, what if I used magnesium sulfide? Suddenly I'm going from 2+ and 2-. So effectively a 4 times increase in size of the lattice energy. So that's what I'm saying. We're going to look at this, if we look at this really at all, as a qualitative scale. So you're going to look at the charge of the ions, and if nothing else, we will look at the size last. You look at the charge first, the size last, just to compare. And that is this chapter. It's a really, really short chapter. So right now we're going to spend a little bit of time looking at some homework. Some of the homework. On Monday, we'll probably continue looking at the homework a little bit, and also look at some tests, some test cribs, some practice tests, because I'm pretty sure already these 2 chapters are all we needed for the test 2 material. So I know it seems like it's coming right down on after the last one. That's because, well, I'll look at what the syllabus says, where we're going to put the test, whether we're going to put it on this material or next. But okay, so let's look at this. So identify the number of core and valence electrons for each atom. So argon would be right there on element 18. All of the core electrons are, you have 10 from neon, and then it has 8 in the core. Looking at beryllium. Beryllium is element number 4, so it would have 2 all the way up to helium and 2 in the valence. Bromine is element like what, 35. This one, I think they probably want you to consider S&P. So you'd have argon and then another 10. Argon, it would be like 18, so probably 28, but I'm going to test this for us. And then 7 in the valence. If I get it wrong, it's because they wanted you to consider the d electrons as part of the valence. No. So they want you to consider the d as part of the core. So this should be pretty simple. Put these in order of atomic radius. This is pretty straightforward. You look at these and you look at, we have carbon, tin, lead, silicon. Carbon, tin, lead, silicon. So all of these guys are in the same column. So you have to think about what does it mean to go down a column when it comes to size. That should be pretty straightforward. Let's see. Arrange the atoms and ions according to radius. Well, you're looking at potassium, plus, minus, and neutral. What do we know about a cation? What do we know about an anion? What do we know about a neutral? We can put those in order of size just for looking at that. What does it mean when you lose an electron, gain an electron, or stay where it's at? Highest ionization energy. So once again, this is a trend based on a column. So you're looking at the column 1A, sodium, lithium, rubidium, potassium. I'm not sure if there's cesium down there. I'd have to scroll down and look. No, there's not cesium, but you could easily look at that and put them in the order. As we move down a table, what happens to the ionization energy? So you put the lowest guy on the bottom, the highest on the top. So far, these aren't going to be too hard. Now, here's our first one that actually thinks, the thinker. The space probe identifies a new element in a sample collected from an asteroid. Successful ionization energies has an attajoules per atom. So it's a small little way of looking at joules or whatever. That's a unit we're not going to worry about. But it's essentially energy per atom. It's a new character of the element given. So where would this fit on the table if they discovered this? So we're looking at where the big jump is. Where the big jump is. So we go 0.5 to 1. Okay, that doubled. To 4. That's okay. Then 5, then 6, then 7, maybe almost 8, then 8. So where does the big jump happen? Well, 0.5 to 1 doesn't seem like a big jump, and 1 to 4 doesn't seem like a big jump, but comparative to here, it looks like the biggest jump is right here. The biggest jump where like almost 4 times jump. So I would say it could lose 2 electrons without touching the core. So those 2 electrons must be in the valence. So I would say this is in column 2. Looking at electron affinity, which one of these guys would gain the most energy? This one's kind of a trick because it includes a noble gas. Noble gases don't want to gain energy. They don't want lithium. You would say, well, lithium would not want to gain energy, but it still wants to gain energy. Still has a greater electron affinity than a noble gas. So let's looking at, just keep looking. Non-metals gain electrons under certain conditions to attain noble gas electron configuration. Many electrons must gain by the element. How many electrons must be gained by the element carbon to attain noble gas electron configuration? So thinking about that. How many electrons gained? That. And then what noble gas would it attain? So if you gain the correct number of electrons, where would it move it to? That seems pretty straightforward. what element forms an ion with this electron configuration. So keep in mind, -2 charge. This is not the pure element. That electron configuration puts it at xenon. This is not the pure element. This is the charged element. So this is saying it has 2 more electrons than it should. So 2 more electrons than it should to get to xenon. What element must this be? So you have to move 2 elements to the left because it should have 2 electrons less. Think about that. Be able to answer a question like that. That seems like a pretty safe bet. For each of the 3 ionic compounds, select which main group element X belongs to. So this is one that's perfect for, say, we've kind of already done X3 PO4. So phosphate is 3 minus. So X would have to be 1 plus. So X would be group 1. Scroll down. Calcium, X2. Calcium is 2 plus. So X would have to be 1 minus, or group 7A. Last one, X2SO43. Sulfate is 2 minus. 2 times 3 is -6. So X2 would have to be 3 plus for each of its X's. So that'd have to be group 3A. So I'd say X was 3 plus, sulfate was 2 minus. And finally, a lattice energy problem. I'll go ahead and do this one, finish this out, and then we'll call it a day. The charge is in size of the ions and then affect the strength. And here's the hint, I think, probably pulls back to the strength and lattice energy dependent on the electrostatic interactions. Consider those how they affect the compound. So straightforward. We have cesium bromide, magnesium fluoride, magnesium oxide, and lithium chloride. So I'm going to actually go to the document cam to show you how I would think about this. F2, MgO, lithium Cl. Okay, go into the doc cam real quick. Okay, there we go. Okay. So we have these 4 guys. I'm going to break these down into cation-anion pairs and look at what is the charges of each guy. Cesium is a column 1A, so it's +1. Bromine is column 7A, so it's -1. Magnesium is column 2A, so it's +2. Fluorine is column 7A, so it's -1. Magnesium is column 2A, so it's 2 plus. Oxygen is column 6A, so it's 2 minus. Lithium is column 1A, 1 plus. Chlorine is column 7A, 1 minus. So for lattice energy lattice, we look at the product of charge. And then second, we look at size. Now, if we multiply these 2 charges together, which gives us the largest number? 1 times 1, 2 times 1, or 2 times 2? 1 times 1. Well, 2 times 2 gives us 4. So 4 is greater than 2, which is greater than 1, which is approximately equal to 1. So this guy is going to have the greatest lattice energy. So this guy is going to be the highest. Magnesium fluoride is going to be the second highest. Now we have to compare 1 and 1 and 1 and 1 are the same. So now we have to consider the size. So what do we know about this guy? Cesium is further down the column. Cesium is larger than lithium. And bromine is further down the column than chlorine. It's larger than chlorine. So cesium bromide is larger overall than lithium chloride. So smaller it is, greater the lattice energy. So lithium chloride would come next, followed by cesium bromide. So always, 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 we're going to compare charge first, and then we're going to go to size. But this is an example of, okay, this is how you would go about doing it. You'd break down first the charge, and then we would break down the size. Do you need to know kappa? No. Do you need to know the actual size? No. We're just going to use these approximate numbers. That's how we'd go about doing that. So we'll start looking at the test come Monday. In the meantime, have a good weekend. Stay safe. Yada, yada, yada.